Hi, my name is Gaster, and I'm from the University of West of England, and I'm going to talk about Audio Anywhere, which is a project I've been working on for a little while now, and in particular in its context of using Faust. So there's a bunch of material that's available for this talk that you can download. There's the slides, there's all the GitHub with all the different implementations, including the modifications for the Faust compiler on my GitHub. There's also a kind of less Faust-focused, slightly longer talk that I did at ADC, which is around this, which might be interesting for people that are interested in this. And I think the video will be available in the future. Okay, so Audio Anywhere is an experimental system for real-time audio built with WebAssembly, but it's not intended for the web. It could be run on the web, but there's other great solutions for that, and this is not the goal of this work. So just briefly, what is WebAssembly? Well, WebAssembly is was developed by Alon Zaki in 2011, and he asked the question, what if we could compile code that wasn't JavaScript, in particular kind of system-based programming language, C and C++, for the browser? And for that, he came up with this thing called Inscription, which is an LLVM-based compiler that produces a subset of JavaScript known as asm.js, which the browsers could then optimize and work around some of the limitations of compiling generic JavaScript. And it's turned out to be really successful. It's amazing how many C and C++ programs they could compile with straight away without even having to port the code and so forth. And this raises the question: why stop there? Why limit yourself to a target of JavaScript? JavaScript wasn't really designed to be a target of other programming languages, even though it's become one. And so in 2015, they worked on this group. All the major browser vendors worked on it together, and they developed this thing called WebAssembly, which has now got a minimal viable product. And it's basically a binary instruction set, quite low level. Looks similar to ARM-based or Intel-based instruction sets that we have on computers today. And it's a virtual machine. It's stack-based, and when it's a virtual machine in the sense that it's not native to any particular machine. There still has to be a translation there that will execute it. And this is what it looks like in textual form. It's actually a binary format by default, because that makes it easier to transmit across the web and so forth. And it shouldn't really be, if you're a computer scientist, be that much surprise to you that it allows you to import functions. It allows you to export functions. It could be data members, any type of symbols, and you can define functions. Here we've got add and subtract being defined, that take parameters and produce results. And because it's a stack-based machine, we'd get those two parameters, for example, in the add function, add them together, load them both onto the stack, and then add them together, the two values that are on the stack, and push the result onto the stack. And it knows then when this function terminates or completes, then it knows to find the result value on the stack. There are lots of other interesting attributes about how WebAssembly works, and I'm not going to talk about that. You can find there's many excellent resources on the web. I'll go into a bit more detail in my ADC talk, but the key takeaway is that it's a low-level language, very simple, and it has this notion of what's called a linear memory, and it doesn't have garbage collection, things like that. It has linear memory, which is effectively, you can think of it like an array of bytes, and where you can offset the values. There's no pointers. It's all offsets into this linear memory. That means they can do bounds checking and things like that to make certain guarantees that are needed for the browser, but also it's actually very powerful to be sandboxed environments on a desktop computer. As I've said, WASM is not limited to the browser by any means, and it's actually there are quite a few attempts and virtual machine implementations that allow you to run WASM or WebAssembly outside of the browser. And the one I particularly focus on is WASM Time here, but there's also WASMer, which is an excellent one, and there's some older ones I like. These two are written in Rust. This is a C-based one, or C++ maybe. And then there's also this tool which converts WebAssembly to a portable C, they call it, and that doesn't make any dependencies on system libraries and things like that, and so it can be ported to different architectures very simply. You still have to go through a compilation phase of producing native code, but that's quite viable at this point. And it's worth noting that there is efforts for something called WASI, for example, which is the WebAssembly system interface, looking at providing portable POSIX APIs to make these kind of accessibility on desktop-based machines or machines with OSs more accessible. However, in this work, I've avoided using that because I wanted to make it as portable as possible to a number of different platforms. And in particular, I was really interested that could it imply that we could compile our DSP code, in this case Faust code, once and run it anywhere. Okay, and that's a bold goal, and I'm by no means the person pushing that to every world. I'm just starting with audio and looking at some of these things, and so I'm sure things will be different one day, but you had to start small, just like oak trees. And this is a quote from Tiffany Aiken, the books of Terry Pratchett's. She's a witch, and I think it's a good point. This is what this work is quite a small start along that road. It's not by any means the answer or doing providing all the answers. So what it does do though is that I've evaluated taking quite a lot of different DSP codes, most of them written in Faust, not all of them, and compiling it down to a single WebAssembly module that can run on these different applications that are built. So one is running on this amazing little microcontroller called a Daisy that appeared over the summer this year, and it's an ARM Cortex. Doesn't have any operating system, and so it's done that, and I've implemented a little virtual machine to run the WASM stuff. And then here it's just a standalone desktop application that I've developed for Windows and Mac OS that loads, uses HTML and JavaScript for its GUIs, and uses Audio Anywhere for its DSP code. And down the bottom here is a really nice application that's developed. It's an open source application on GitHub developed by Ryan, and it's a kind of, it can load different modules, and all of his modules are written in C++, and it can also load VST modules, but I've extended it so that it can load in Audio Anywhere modules, which is this little logo here, and you can see a couple of them chained together, and this is a little 4-track sampler that records them and so forth, and things. And this is literally just loading the WASM modules. It's got a JSON description of the UI interfaces that connect and automatically generate them within the bespoke model. And so it can run on Windows and on OS X, for example, and it loads exactly the same WASM module, exactly the same JSON UI interfaces, and so it's completely portable in that sense. So what does it look like? Well, we take some DSP code. I've got DOS DSP code because most of it's Faust, like I said, and we compile it once, in this case by a modified Faust compiler that actually generates Rust and then generates the WASM from the Rust. And we can run it on these different platforms. And if we weren't doing that, if we were using the native approach, we'd have to compile it n times, once for each platform. And that's not necessarily a bad thing, but I was really wanted to explore the capabilities of that. And one of the real benefits of being able to compile once is, assuming that we can get the performance, is that we could minimize updates. We could just transmit a single WASM file and it would update it, and like that, rather than having to do a whole new binary and transmitting that and doing the testing related to that. It avoids issues with OS updates and things like that, potentially. So an Audio Anywhere module, the most important thing is this WASM code here, which is completely portable, and then you'll have some sort of interface. There's different ones. As I said, there's a HTML, CSS plus JavaScript interfaces that I support. There's also a JSON module UI format that I support too. But that's really independent, and I'm not claiming that that's that. Certainly not novel, but it's also not that interesting to compare to the WASM code. We use JSON just to bundle that up. But the most important thing here is that there's a single hosting application for a supported platform. And this, of course, is where a lot of the value would go if you were making a production-based system around this. Okay, so how's the code actually compiled? Well, we take our Faust code at the top here, we translate to Rust, using a modified version of the Faust compiler, and we generate WASM, and then connected to that is some sort of UI description. Okay, but the key thing here is that there's these hosting applications are written once and run on the different platforms that are supported, for example. To make all this work, WASM really only exposes C, allows you to expose C-based interfaces. And so I'm particularly interested in Hourglass API-based design, where you kind of have a very small C-based API, or at least an ABI interface, and then you can build more complex APIs on either side. On either side of that, so your implementation can be as complex as you like inside the lower part of the API, and then at the top you could have a Rust interface for that API, a C interface, a C++, or whatever. Okay, so you can expose all those things as you want, but that's a kind of separate issue. The actual level where the code is, where application transfers control to the library happens at a C interface, and we benefit from that because WASM really only supports those interfaces. So, for example, you're all being familiar, hopefully, at a Rust conference with, the Faust conference, with what Faust would produce, and it's very similar, but at the C level. So here we have an init function. You can get the sample rate, the inputs, the outputs, number of voices, and so forth. You can see here that the init function is the only function that doesn't take a module, and that's because it generates a module. So basically it's an opaque handle or opaque pointer, but we can talk about it as handles, just like OpenGL or OpenCL do. You basically you get back an opaque handle that you can then pass across the API boundaries. And because it's opaque and it's a UNIX64, we don't have any work whether it's 32-bit architecture or 64-bit architecture, for example. And we're quite careful. This is written in Rust, but you could write it in C, to make sure that we're very explicit about the size of types and the type of type that we're using, and so that and these match closely with what's supported in WebAssembly, but also what is portable at the level of C as well. So these two things are go hand in hand with one another. There's lots of other functions like get parameters, set parameters, those sorts of things, handle note on, note off messages, so forth. None of this should be a surprise, hopefully, if you're familiar with the Faust APIs, because it's done really well there, and many other APIs are very similar to this. Okay. There is a couple of things to note. The compute function doesn't take any buffers, just takes the number of frames that we're calculating, or the buffer size, and the buffers are actually handled within the runtime itself and within the audio anywhere modules, because we want to be able to chain modules as an audio graph inside the WASM code, because that allows us to do optimizations that wouldn't otherwise be possible. You'd have to do that either in the Faust compiler or in another compiler, whereas we're here, we can actually optimize the audio graph at the level of WebAssembly. And so Soul, if you're familiar with that, it does something similar, but does it at the it has an intermediate language, which I can't remember what it's called, but it has a similar design philosophy that you could do that kind of graph-based optimization there. Okay, as I've already mentioned, they're written in Faust. That's why I'm at this conference, and the DSP is most of them, not all of them. I've written some in Rust, in particular. A couple of my students, or one of my students, Harry, he has implemented some physical models on OpenCL and in C++, and I've ported those over to Rust so that they can run in audio anywhere. The implementation takes the Faust compiler, compiles it to Rust, and I'll talk about what that is in a second, but you could equally compile Rust, you could compile C++, any language that generates WebAssembly would be used equally, is suitable. There may be some drawbacks if you have to have garbage collection, those sorts of things, but that's the kind of implementation detail of a particular choice. And then we can run these on the different architectures as we so choose. As I've already said all of the actual input and output buffers are generated by the Faust compiler and allocated once statically, and that allows us to manipulate them and update them. And then, of course, we generate a DSP struct that will then have the main aspects of the thing. And most of this is very similar to what Faust already generates. I've tweaked it a little bit, and you can see more details about what the changes are But again, most of that is the Faust compiler already did it. There's some optimizations and things that I'm not going to talk about here, but the paper goes into. Why do we use Rust? Well, Rust is particularly a close friend to WASM, partly because it's often developed by the same group of people and industry activists and so forth. But it also provides a route to auto-vectorization, and that's one of the modifications that we've made to the Faust compiler, is that it generates, with the work of Stefan as well, it closely generates code that can be auto-vectorized by the Rust compiler, in particular by LLVM, such that it can use the WASM 128 SIMD instructions and get all the benefits that you get from SIMD instruction selection. And plus all the libraries that are written that support are all written in Rust too. There's a little tool called Faust to Anywhere, which allows you to compile DFP code. There's a fork of the Faust compiler, and you can find that on my GitHub. That supports the changes that were necessary. As I said, there's not that many. There's a few, but nothing really that surprising. Okay, so for the last part of this talk, let's skip to the demo and show you what this actually looks like. Okay, so I'm just going to give the demo in Bespoke, and so we'll just start that up in here. So Bespoke's a nice application. It has all these different instruments. So Ryan has all these C++ based instruments written here. He's got some audio effects, and he's also got the ability. So, for example, you can add a MIDI controller or a Step My Keystep Pro, and then you could add in some of these things. And then at the end here, I've extended Bespoke to know about these additional ones. In particular, I've got it so you can have a audio anywhere modules that are available. And these are the ones that I've implemented, a bunch of different ones. So, for example, we could take this VO1, which is a simulation written in Faust of the Casio VO1 instrument, and we could wire that up to the outputs. We could wire up our MIDI controller here, and then we could start playing some notes. And you get the gist, and we can these are all, and this is all written in Audio Anywhere, and then we can add in say we've wanted a reverb, for example, and then we could just pop that onto there and connect that to there. Initially there's no difference, but we can turn on the vibrating force and we'll start to get some noise. You can hear the kicking in once we're there. And there's all sorts of different instruments I've written, and all of them, well, not all of them, but most of them are all Faust based. So that we've got a nice polyphonic analog synthesizer here, which it's the standard things, the wave-based oscillating change the wave, filter, resonance and so forth, and then we can hear that it's so polyphonic and so forth. Again, these are all written in Audio Anywhere. They'll load in the desktop application I showed you. All of these ones run on the Daisy 2. They probably wouldn't all run together. I haven't tried that, but I've certainly had the VL1 and the Reflect running together on the Daisy, and it's a microcontroller, so at some point, it doesn't matter how much portability you've got, you're going to run out of juice. Okay, and so that's an important aspect. And as I said before, there are some instruments. So this, for example, is just written in native Rust, and I'll just change the octave a bit. And this is a physical model simulation, which actually this one is just using native Rust, but it's also ported to C++, so it's obviously doing a strings-based simulation. And here we could have, we have it running on the OpenCL. I don't, but my student have it with 12 strings, for example. And so obviously that's not Faust based, and potentially you could do it in Faust, but it's to highlight the fact that it's the WebAssembly that's portable, it's the Audio Anywhere API that's portable, not necessarily the Faust is just being used as a tool, but it's a really good tool, and modifying the compiler was so straightforward and simple that it was really beneficial. Okay, so to there, I think that's the final thing. So just very briefly to conclude, and I know I'm very wary of time, how does it run in practice? Well, actually, with the modifications to the Faust compiler, you can to generate this optimized Rust, which is using the kind of ways that avoid aliasing and thus avoid bound checking and things like that in Rust. We can see that we can actually get very similar performance for with optimized C++. And it's 20 times faster than the earlier work on the Faust to Rust compiler, and but it's comparable with C++. And if we look very briefly about what kind of times we might expect for the actual virtual machine actually running the WASM code compared to running native code, you can see here that for a null function call, then this is microseconds, so we're not talking hardly anything here, and it's definitely a bit slower when you look at compared to native code, which is virtually nothing, but it's very low overhead, and we can see the same for sine oscillators. Again, we're down in microseconds here, and the performance is really quite good. This one here, with using SIMD, is comparable. This is using SIMD 2 in native C++ code, and the WASM runtime gets a bit slower because it doesn't support SIMD, so you can see the benefits of using SIMD in WASM code too. And copying in and out is again, the performance is clearly less than it is compared to native copies because there's nothing happening there. But for a buffer size of 64, it's tiny. Right? It's negligible, and so it's looking very promising. And there's still work to do. There's issues with denorms and things like that have to be handled in software at the moment that the compiler needs modifications for because WASM doesn't support that. But generally, it's looking very, very promising. Okay, there's more information on the project site. Please check that out.